I'm talking to you today about WebAssembly and asking the question, is this going to be the death of JavaScript? And yeah, it might not be the best meetup to ask a question like that. If you feel like throwing something at me, that's fine. Just wait till the end. That's all cool. So I'm going to start off in typical fashion with a brief history of the web. And I know the web is a complex set of technologies. I'm mostly going to be looking at JavaScript. And as I think most people who've worked with JavaScript for a while know, the language itself was invented in a very short space of time by a chap called Brendan Eich. He invented it in just 10 days. And back in 1995, the web was a very, very different place. It wasn't the kind of dynamic, single-page app, React-type environment that we know right now. It was mostly static pages, the occasional form, and JavaScript was there to just add a little bit of interactivity on top of an otherwise pretty static web. Since then, other languages have come along, Java Applets, ActiveX, Flash, you might have used some of these, Silverlight, my apologies if you've used that, Dart, and so on. And that's it, that's the history of the web done, because 2018, it's still JavaScript, it's still only JavaScript. JavaScript is the only language which is officially supported by the web. But the interesting thing is the way that we're using JavaScript has changed a lot in the 20-odd years since it was originally invented. I guess, without going into too much detail, one of the things that I've observed is that we collectively write a lot of JavaScript. And when I say a lot, I mean a lot of JavaScript. Just the other day, I started up a new React app, so I used the Create React App package. So this is me creating a new application and then finding all the JavaScript files within the project and doing a line count. 79,000 lines of JavaScript. That's a lot of JavaScript. And the thing is, we're using JavaScript for far more than just adding interactivity on web pages, which is the world that Brendan Eich was creating JavaScript for. We're using it as build tools, we're using it on the server, we're using it on mobile devices, we're using it all over the place. But the weird thing is, the way that we're using the language itself has changed quite a bit. Many years ago, I guess when I first started using JavaScript, it was quite simple. You'd open up a text editor, you'd write some JavaScript, it would be served over HTTP, and exactly the code that you had written would be executed within the browser. That doesn't happen very often these days. Typically, the code that you write will be transpiled, it will be minified, it will be bundled, it will go through all kinds of really quite advanced transformations. And by the time it lands in your browser, it will look a bit like a garbled mess. And that's led a few people to consider JavaScript to be the assembly language of the web. It's a compilation target, as well as the language we use to write our applications. But this is where, sorry, I moved my cursor. This is where the problems start to surface, because JavaScript actually isn't a very good assembly language. And it's no surprise. Again, reflecting on the context within which it was invented in the first place, it was never designed to be an assembly language. It was never designed to be a compilation target. And to understand why it's a bad compilation target, why it's not a good assembly language, you have to understand a little bit more about how JavaScript is executed within the browser. So this is a diagram that I took from a Mozilla blog post where they were giving a rough overview of how JavaScript is executed within the browser. So the first bit on the left-hand side is a bunch of characters come along over HTTP, and they're parsed into a thing called an abstract syntax tree. It's a tree-like representation of your code. After that, it generates some bytecode, which is then run within an interpreter. And then this is where the really clever stuff starts happening. Many years ago, that was it. That was the way that JavaScript was executed. These days, a lot of work has gone into optimizing JavaScript. So what will happen is the runtime will start to look at your code, look at the execution, and make certain assumptions. If you've got a function that is always called with a pair of integers, for example, it will generate an optimized version of that, and the execution of that function will become faster. And I think it was the Safari browser has something like 4 different tiers of optimization, and your code sort of moves up and down these tiers. So as it can spot optimizations, it moves up a tier, but if the assumptions it makes about your code is false, it has to push it back down again. It's really, really complicated, and as you can imagine, this isn't an efficient compilation target. And how does this actually manifest itself? One of the things that, as a JavaScript developer, most of us, or pretty much all of us, are concerned about is the execution speed of our code within the browser. One of the most important things, something that people have been focusing on a lot recently, is the time to interactive, the time it takes to load all your code and actually start doing something. And this is a timeline that I shamelessly borrowed from this fantastic blog post by Lynn Clark. It's well worth a read. She does an excellent job of describing why WebAssembly is needed. But I'm just grabbing this diagram here. This is a timeline that approximates the execution of JavaScript within your browser. So the first thing it does is it has to parse your JavaScript. The next is it has to compile and optimize it, and then potentially it will have to re-optimize it, and then afterwards you've got a certain amount of execution and garbage collection. The timeline you see here, the parse time, the compile time, the optimize time, has a significant impact on how long it takes for your application to actually execute and be interactive. So this is again why I'm saying that JavaScript isn't a good assembly language. This isn't, if you were designing it from scratch, you wouldn't design it like this. And I guess this little quote here I think summarizes it quite nicely. This is a quote from the team that created WebAssembly. And they mentioned that the web has become the most ubiquitous application platform ever, and yet by historical accident, the only natively supported programming language for that platform is JavaScript. And this is coming from a bunch of guys who are web developers, and they love JavaScript. So they're not against the JavaScript language as itself, but the situation we've found ourselves is a weird quirk of history. So that brings me on to WebAssembly. If you look at the WebAssembly specification, the WebAssembly website, they describe it as a new portable size and load time efficient format suitable for compilation to the web. So it was designed specifically to solve some of the problems I've been talking about. Now, hands up if you've heard of Asm Js before. Okay, that's good. So an interesting part of the history of WebAssembly is quite tightly related to Asm Js. Don't worry if you've not heard of it before, it doesn't matter. I'll give you a quick illustration of what it is, and hopefully that will help you understand some of the design goals of WebAssembly. So Asm Js was a bit of an experiment. It was actually a bit of a wacky idea that was created by Mozilla, I think around about 5 years ago. And at that point in time, there were various other plugin-like technologies being considered. The standard plugin model is you take some other runtime and you kind of bolt it onto the side of the browser. That's how plugins worked. And at that time, there were other people considering other plugin-style models. Whereas the Mozilla team came up with this slightly crazy idea of why don't we create this sort of virtual runtime that sits within the JavaScript virtual machine. So they said, okay, we need memory, so we'll just have an array. That can be our memory. We need instructions, so we'll create effectively patterns within our JavaScript that represent those instructions. So I'll quickly illustrate what it is and then show you why that is a great demonstration of a slightly better way of doing things. So here's a bit of code. This is some Asm Js code. Don't worry too much about the detail. At the top, this is a function written in C that does your standard Fibonacci calculation. I'm compiling it using a tool called mscripton into Asm Js, and that's what you see at the bottom there. So Asm Js is JavaScript, but it's a particularly peculiar looking kind of JavaScript. I'll highlight a few things. I won't go into all the details, but the first thing you'll see here is the reassignment of the arguments to this function. So a equals plus a. So typically you'd use that to kind of coerce something to be a number. B equals b or 0, which means that it's exactly the same as it was previously. These are type hints. These are telling the runtime that one of these is a float and one of them is an integer. You can see at the bottom it's returning plus c. Again, you can see the pattern here that res in my C code is a float. You can see that we've got in the JavaScript code a for loop. Asm Js doesn't support for loops. Here you've got a do while instead. So that all looks a bit crazy, and you might be asking, why on earth would you do that? Getting back to the way that JavaScript executes within the browser, you can see what they were trying to achieve with Asm Js. So what happens within a browser that understands it? Well, firstly, if the browser doesn't understand Asm Js, it doesn't matter. It's just plain old JavaScript, and it executes as normal. However, if the JavaScript recognizes Asm Js, and it does that by looking at this use ASM literal string at the top, What it does is it starts doing the usual thing. It parses it into an abstract syntax tree, but then immediately it spots the patterns. It effectively reads the Asm Js assembly language and immediately is able to push it right up to quite a highly optimized version of the code, skipping some of the quite time-consuming interpreter steps and optimization steps. So as you can imagine, this is quite a neat idea, but I think Asm Js was only ever put together as a technical proof of concept, because one of the things they could never get around is the very first bit at the beginning, the parsing the JavaScript language. And as you can see, Asm Js is itself pretty verbose. So as you can imagine, parsing it to the abstract syntax tree has got quite a lot of overhead. But Asm Js was a great proof of concept that there might be a better way of doing things. And their early demos were really quite impressive. The mscripton tool that they use also had logic in it to convert OpenGL code into WebGL code. And they were able to take some game engines and do some pretty impressive things. So Asm Js pointed people towards a different and interesting approach to solving this problem, which was quite different to the standard sort of plugin model. As a result, the WebAssembly working group was formed, and it was formed in 2015 with representation from all the main browser vendors and a bunch of others. And quite impressively, within the space of 2 years, they managed to design their MVP scope for WebAssembly and get it released in the wild. So in November last year, it was turned on in all major browsers without the need for flags. So it's officially out there in the wild. It's also in Node version 8 and beyond. And just earlier this month, W3C published their first public draft as well. So they managed to get this done in a very short space of time. And I think it was mostly because Asm Js effectively created a blueprint to demonstrate some of the concepts here. So I've talked a lot about WebAssembly, but I haven't actually shown you any WebAssembly. So I thought the best way to do that was to actually show some code and talk around the code, just so you get a better idea of what it actually looks like in real life. So switching to code, this is obviously where it all goes horribly wrong. Okay, so I'm going to start with a very, very simple example. This is a function that adds two numbers together, and even though this is VS Code, that's actually C, which is horrible and dirty and makes me want to wash my hands. But there you go. There's an add function. And what happens is, with my tool chain, I'm not going to go into too much detail about that. My tool chain is compiling that into WebAssembly. And there are two distinct formats that you can use to view your WebAssembly. The obvious one is, tiny, is in hex. So the output of WebAssembly is a binary format. So again, recalling how JavaScript is processed by your browser, it no longer has to parse the characters into an abstract syntax tree. It's a compact binary format. But the more useful way of looking at it is actually, they've changed the file extension for this. It's the WAT format, WebAssembly text format. It's a shame they didn't go for WebAssembly text format WTF as an extension. That would have been awesome. But anyway, this is my C code, so I'm adding two numbers together, and this is what it looks like as WebAssembly. So a few little bits and pieces here. We've got the concept of memory. So memory within WebAssembly is very similar to the memory concept they invented with Asm Js. Memory is a contiguous array of bytes. And that memory is actually shared between the WebAssembly runtime and the JavaScript runtime. So you can make writes to the WebAssembly memory from your JavaScript code. It defines functions. It's got a whole load of instructions. There are about 60 odd instructions, and it works as a stack machine. If you've done any programming with some kind of assembly language of some sort, the full instruction set will look quite familiar to you. WebAssembly can also export and import functions. So you can export a JavaScript function from your WebAssembly module. So you can export a WebAssembly function from your module and invoke it from JavaScript. And vice versa, you can import a JavaScript module so that it can be executed by your JavaScript. So that's my WebAssembly, and we've got the binary format. And I'll show you how it's actually loaded, instantiated and executed. Now, because I can't be bothered with creating a HTML page to house this, I'm just doing it within Node, but it's pretty similar within the browser. So we're loading the WebAssembly binary format, and we're constructing a module from it, and then from the module we're creating an instance. From the instance we can invoke the exported functions. So here if I execute add, it tells me that 2 add 3 equals 5. So here I've gone from JavaScript, it's executed a WebAssembly function within the WebAssembly virtual machine and returned the result. That's all pretty straightforward. I'll show you now some of the areas where it gets a little bit tricky. And now I feel like I'm showing you a bit of a tip of the iceberg in that it's not a simple case of just writing a whole load of code in WebAssembly, creating an API layer and invoking it from JavaScript. At the moment it's relatively challenging to do that. One of the reasons for doing that is that WebAssembly has a very small number of built-in types. It only has 4 types and they're all numeric. So it's got 2 floating point and 2 integer types. What that means is if you want to do something with something a little bit more advanced like strings, it gets quite complicated. So my next little demo is just something which returns a simple string from my WebAssembly function and renders it from JavaScript. So I'll just pop back there. Okay, so this is my C code. So what I've done is I've created a hello Asm string, which is referenced as a character pointer. And I've got a function which is getMessageRef. So what that's doing is returning the reference to the message. If we look at the compiled output, it's a little bit more complicated this time. We've got these things called data sections within our WebAssembly module, and these are basically ways of instantiating your WebAssembly module memory to a known state. And here you can see it's actually writing hello Asm. It's writing something else, which I think is the offset to... actually, I'm not sure. I'll have to check that one. It's writing something else. And here is how it's actually executed within JavaScript. And here you can see that simply by changing it from an example based on integer types to strings, things get a little bit more complicated. So we've seen this bit of code before. This loads our WebAssembly binary and instantiates a module. But now, to return the string, the getMessageRef function isn't returning a string, it's returning an integer, which is an index to the location of that string within linear memory. So I'm having to get hold of a reference to my linear memory, create a buffer, and iterate over that buffer, populating it with going byte by byte across my linear memory, reading the data out. And if I execute it, it does indeed say hello Asm. And that's by all means not an exhaustive demonstration of WebAssembly, but hopefully it gives you a bit of a feel for how you use a WebAssembly module from within JavaScript and some of the current limitations that there are. So a little bit more on the WebAssembly architecture. So WebAssembly itself is a stack machine. As I've mentioned, it has 4 built-in types, 67 instructions. Importantly, it's designed to support streaming compilation. So there are some features that are specific to WebAssembly which reflect the context it's used within. For the vast majority of use cases, your code is being streamed over HTTP, so it makes sense that WebAssembly can be compiled in a streaming fashion. And what that means is your browser is able to chop up the WebAssembly module and compile it in parallel on multiple threads. So again, it's been designed to be very, very fast. It also has some very simple validation rules. JavaScript and any other web-based language has a lot of validation rules that ensure security. WebAssembly is just the same, but again, they've been designed in such a way that they can be processed in serial as it's streamed in. And as I mentioned before, it exports, imports functions, and has a concept of shared linear memory with JavaScript. Now, one of the first questions that people ask when they look at WebAssembly is, oh, great, this is going to be super duper performant. It's going to be really, really fast. And I must admit, I've read a lot of blog posts which make some quite impressive and, to be honest, quite incorrect claims about the performance of WebAssembly. I've seen blog posts claiming that it's 100 times faster than JavaScript. Unfortunately, most of those blog posts suffer from the classic problem of doing micro-benchmarking and either benchmarking the wrong thing as well. So what I did was created a slightly more representative test case. I created a Mandelbrot and rendered that using C, JavaScript, and a bunch of different mechanisms for generating WebAssembly modules, and I compared the performance of them. And as you can see, the black line here is the native performance. So that's my C code compiled directly on my Mac and executed natively. And the interesting observation immediately is, wow, JavaScript is really, really fast. It's only about 20% slower at rendering a Mandelbrot, and that's because of the many, many years that's gone into the runtime optimization for JavaScript. Disappointingly, when I ran it within WebAssembly, it was actually a little bit slower, and using Wasm, assembly script, and a few other different approaches, I eventually, through a number of optimizations, managed to make it just a little bit faster than JavaScript. So I must admit, I was a little bit disappointed by that result. I've had a look at other benchmarks and other results, and most importantly, the paper that was published by the WebAssembly team. The accepted sort of general feeling is that WebAssembly should be around about 20 to 30% faster at runtime execution than JavaScript. But because JavaScript is really quite fast, there isn't that much of a performance gain to be made. Where they expect WebAssembly to beat JavaScript significantly is the parse time and the initial compilation time. So the time to interactive with WebAssembly should theoretically be a lot less than with JavaScript. So in the future, one of the things I mentioned was that WebAssembly was developed over a really quite short space of time. And partly that was because they had Asm Js as a kind of reference implementation. Another reason is the current WebAssembly release is very much an MVP. They were quite aggressive about ensuring that they had a very small set of features so that they could release quickly. And the idea is that they're going to be releasing new features over the coming years. So some of the things that it doesn't have at the moment is a garbage collector, and I'll explain why that's a bit of a pain later on. In the future, it will also have threading support, a thing called host bindings, which is a way, as I showed you, the interface between JavaScript and WebAssembly is a little complicated at the moment, and if you want to start doing DOM manipulation from WebAssembly, that's hard. With host bindings in the future, that will become a lot easier. So one of the final things I want to look at is WebAssembly language support and what some people are actually doing with the language. So I showed you a little bit of writing a bit of C code as a way to show you what WebAssembly actually looks like, the text format and so on. But most people aren't going to write WebAssembly in its machine code, in its binary format or in the text format. Most people are going to want to use a language, maybe C, maybe not, Rust, Go. People are going to be using other languages and treating WebAssembly as a compilation target. So I'm going to quickly look at the different languages and their current level of support. So the first one is C or C++, and this is the very first language that gained WebAssembly support, and again that's due to its heritage from Asm Js. There's a tool called mscripton that you can use to compile C to WebAssembly, and mscripton does a lot more than just a straightforward compilation. It has, as I've mentioned, it's got the OpenGL to WebGL bindings, and it's got a whole load of other things that make it quite easy to take an existing C code base and compile it to WebAssembly and put all the glue that's required around it to actually make it work. And as I mentioned, it was originally used to create the Asm Js concept. Some of the practical things I've seen people do with it, there's a company that have a thing called PDF Kit. It's basically a PDF renderer, and just last year they started exploring the use of WebAssembly. So they've got a C++ code base, and they explored the use of WebAssembly as a way of using exactly the same code base to do PDF rendering on the web. And they found it quite a good experience. They managed to create something which I think they're going to actually ship as a product with very good performance. This one's a fun one, JSC. So the JavaScript core, which is the JavaScript machine that runs within WebKit, is itself written in C++. Now, using mscripton, you can compile C++ to WebAssembly. So what that means is you can take JavaScript core, compile it to WebAssembly, and then run it on top of your JavaScript virtual machine. So what this is the Safari JavaScript virtual machine compiled to WebAssembly running on Chrome, which is great. It's exactly what you need. Finally, one thing you'll probably notice here is at the moment, a lot of people are essentially experimenting with this technology. You won't find a huge number of really practical use cases yet. I think that's still to come. Although where I work at Scott Logic, we've done a bit of work with a company called Active Financial, and they provide They provide market data for people that need high-frequency data, so people that are doing algorithmic trading, for example. And all of their distribution logic, all their serialization logic is written in C and C++. And they've been getting a lot of requests from their clients who want to start using it, consuming this data from within JavaScript, either perhaps AWS in a Lambda function or perhaps within the browser. So we help them take their C++ code, compile it to WebAssembly, and use exactly the same code to parse their packets of data and deliver their high-frequency data to the web. So that's something that we were able to achieve with WebAssembly. Oh, that should say C#. That's a mistake. Anyway, so C, C++, that's the story. Java and C#. These ones are a little bit more challenging because, I'm sure you're aware, Java and C# are languages that both rely on garbage collection, whereas C, C++, you manually manage the life cycle of your objects. And because WebAssembly doesn't have garbage collection yet, that means it's quite a problem, it's quite a challenge to take Java and C# code and compile it to WebAssembly. There's an experimental project called Blazor that's become an official, I think, ASP.NET experiment, which uses Mono, some of you may be aware of Mono, as a way to run Java and C# within WebAssembly. And what they're doing is they're experimenting with a couple of different ways of doing it. One of them is interpreted mode. So they've basically taken the runtime and compiled it to WebAssembly, and they're executing C# DLLs directly within the browser. The other one is ahead-of-time compilation. So they're actually compiling the DLL directly to WebAssembly. And they're experimenting with these two side by side. Blazor is a project that wraps around Mono's WebAssembly support, and it's a fully featured single-page application framework. So there's a lot of C# developers getting quite excited about the potential of Blazor. I don't have anything practical to show on C# and Blazor because it's very, very new, and I don't think anyone's done anything practical with it quite yet. So I guess one of the final ones to talk about is JavaScript. So why shouldn't you compile JavaScript to WebAssembly? And there's a lot of people writing React applications and all kinds of other JavaScript-based applications. And you look at the features you get with WebAssembly and you think, yeah, I'd like some of that. I'd like my JavaScript to parse more quickly, to be optimized immediately. So there are a lot of people trying to find creative ways to compile JavaScript to WebAssembly. And obviously, there are even more challenges there. So firstly, you need a garbage collector. Secondly, it's not statically typed. So you've got typing as a bit of an issue. There are a couple of projects that I've been keeping an eye on that are trying to tackle this. First is called Walt, which is a JavaScript-like syntax for WebAssembly. So what they've done is they've taken that text-based format which I've shown you and tried to map it as closely as possible to JavaScript. So it's a thin veneer on top of the WebAssembly text format. The other one that I've actually had a bit of a go with is AssemblyScript. So in order to solve the typing issue, that's pretty straightforward with JavaScript these days. You've got things like Flow and TypeScript that introduce typing. So with TypeScript, you can enforce typing of your code and use a very similar compilation path that you do for C and C++. At the moment, that project is in its early stages, and they're currently awaiting news of when garbage collection will appear within WebAssembly to make some fairly critical design decisions about how they tackle that. I've actually got a bit of a demo. Hopefully I typed in the Wi-Fi password. Oh. So has anyone used D3 before? Yeah? Cool. Yeah, everyone loves D3. So this is a D3 force layout. But what I've done is I've taken D3 force layout and taken all of the algorithmic code and rewritten it using TypeScript and compiled it to WebAssembly. So basically, the standard sort of n-body algorithm and the kind of Hooke's law spring concepts are all being computed here within WebAssembly using TypeScript. And it was quite an interesting experiment for me to see how easy it is to take a JavaScript application that wasn't written in TypeScript, add type information to it, and then compile it to WebAssembly and work out how to manage the interface between the two. So actually, if you scroll down, if I scroll down, you can see it supports exactly the same API as D3 itself, but all the computations being done in WebAssembly. That was good fun. I enjoyed that. Actually, one thing I'm going to do is I'm going to get rid of that demo because it's got a memory leak. Yeah, I know. The final one I want to briefly touch on is Rust. Has anyone used Rust here before? No? definitely the wrong room for that. Oh, a few, yeah. So Rust is gaining popularity quite quickly. If you ever have a look at the sort of metrics, Stack Overflow does a survey every year and they do quite a lot of data analysis, and Rust seems to be a programming language that makes people really, really, really happy. So it's a modern language, it's a very, very popular language. Significantly here, it doesn't require a garbage collector. It's got quite an interesting memory model that has the concept of ownership. So every object that's allocated on the heap is only ever owned by one reference at one point in time, which makes it very, very easy to reason about memory and clean up memory. It's hard getting your head around it initially, but it's a good concept. So within Rust, what they did was they used the mscript and toolchain and are actually investing time in creating some better toolchains. And I found this quote actually from someone within the Rust community who says, "We're poised to be the language of choice for WebAssembly." And the reason for that is it's a much loved language, and because it doesn't need a garbage collector, it's actually in a great position for being compiled to WebAssembly right now. So I had a bit of a play with it myself. I created a Chip 8 emulator. So Chip 8 is a pretty old engine for playing arcade games. I say engine, it was one of the very first virtual machines actually. It was developed by someone who at the time came up with a concept for a virtual machine for playing games that could then be incorporated into a number of the current computers at the time. It was a great idea, wasn't terribly successful, but it's great for people who want to experiment with creating emulators because it's actually quite a simple machine to emulate. So for me, this was great fun, having a go at Rust. I'd not used Rust before, so trying to do Rust, write an emulator, which I'd not do before, and then compile that to WebAssembly, that kept me up a lot of nights, but that was good fun. But having said that, people are doing some really practical and useful stuff with Rust and WebAssembly. And again, a lot of this is coming from Mozilla. So in a very recent blog post, they've talked about some of the work they've done on source maps. So source maps is, if you're not aware of what source maps is a technology that allows you to map that highly mangled version of the code that runs in your browser to the source code that you created in the first place. So source maps are a way of mapping from one representation of code to another. And source maps are, as you can imagine, quite computationally intensive, but the most popular source maps library that supports parsing and understanding source maps is all written in JavaScript. And the team behind it decided to take some of the most performance-critical logic, rewrite it in Rust, compile it to WebAssembly, and then evaluate the performance. And you can see here, one of the performance metrics they were looking at was the time it takes from setting a breakpoint to being able to actually inspect your code. So basically to be able to parse, I don't know if parse is the right word, but understand the source maps and map the breakpoint back to your original code. And as you can see here, the WebAssembly performance, I know the text is a bit small there at the bottom, but the WebAssembly performance is these little blue clusters. So a couple of observations. The first one is clearly WebAssembly is quite a bit faster, in the order of 2 to 3 times faster. But another interesting aspect here is the JavaScript performance. You'll see quite a spread in performance. And that is because, again, of the nature of the way that JavaScript is executed. It goes through multiple tiers of optimization, where it might be optimized and then de-optimized. And what that means is your runtime performance isn't terribly predictable, whereas within WebAssembly, the runtime performance is highly predictable in comparison. So that was a fantastic blog post and a really interesting read. And the interesting thing is, even though this was done as an experiment, if they're happy with it, if all the unit tests run, they can put that in production now, and everyone who uses source maps directly or indirectly is then going to receive the performance boost. So finally, I want to do a bit of crystal ball gazing. So as I've shown you, that the current state of WebAssembly is variable depending on language, and in terms of what people are doing with it, again, there's lots and lots of experimentation. But now I think we're starting to see the signs of where it's actually going to be used in the future and how it's practically going to be used. So my prediction for 2018 is, as you can imagine, lots more creativity, mostly coming out of languages like Rust, but we're also seeing a lot of creativity with C#. I have a feeling the Swift community are going to be very, very keen on this, because Swift has a lot of common attributes with Rust. It's a modern language, it's quite a pleasant language to use, and also using Arc, automatic reference counting. It's got a memory model that's quite compatible with WebAssembly. Also, within 2018, I don't know if you've noticed, 2 days ago there was a new Webpack release, version 4, and that included WebAssembly support. So WebAssembly as a toolchain now allows you to import Rust directly within your code, and Webpack, because it's magic, will do its magic and the right thing will pop out the other end. Hopefully, if you get your configuration right. So yeah, if you get your configuration right, it's great. If it's not right, then it's hell. But I also think that within 2018, you'll start to see WebAssembly sneaking into your daily workflow without actually knowing it. So as I showed you right back at the beginning, when I create a React application, it adds 79,000 lines of JavaScript to my machine, and most of that code is being used at build time. Very little of it is actually being used at runtime. I think that 79,000 is going to start going down as people start to use WebAssembly to hit performance critical parts of your tooling. Another thing I think you're going to start seeing is native node modules using WebAssembly. I don't know about you, but I find it quite frustrating that the workflow involved in using node modules that have native code. There's a lot of friction there. Now, there isn't a terribly good reason to do that anymore. You can actually ship WebAssembly instead. So 2019. Within WebAssembly itself, I'm pretty sure we'll start to see garbage collection, host binding, threading. We'll start to see WebAssembly itself become a lot more powerful. As a result, C# and Java, some of the languages that require a garbage collector, will become first-class citizens of the sort of WebAssembly ecosystem. I think we're also going to start seeing Asm UI frameworks. So we're going to start seeing UI frameworks that are targeted, that are entirely written as WebAssembly and geared towards perhaps C# or Java developers. And we're already starting to see that. I saw a project which was called Asm DOM, which was a virtual DOM, so modeling the React concept, a virtual DOM written in C++, compiling to WebAssembly. Whereas next year, I think that'll actually start to become a practical option. Also, I think we'll see more of our general plumbing move to WebAssembly. For example, again, using React as an example, it does some computationally intensive tasks to do the DOM diffing. Why not put that in WebAssembly? Other frameworks, for example, there's a thing called the Glimmer VM, which is a templating engine, which is in one of the UI frameworks whose name I can't remember, but I'm pretty sure that will move to WebAssembly as well. Interestingly, though, I think we're going to start seeing Rust, Go, Swift, and other languages start to gain some web market share. You might think that's a good thing, you might think that's a bad thing, but I honestly think it's going to start happening. 2020 and beyond, again, I'm going to go back to that quote. The web has become the most ubiquitous platform ever, yet historically, by accident, the only language that is supported by the browser is JavaScript. I think in 2020, we're going to see that being challenged. JavaScript will no longer be the only language of the browser and the web. I also think people are going to start making significant progress towards compiling JavaScript directly to WebAssembly, again for the very reason that JavaScript is a perfectly good language for writing web applications. There's absolutely nothing wrong with it. But at the same time, as JavaScript developers start seeing Rust developers and Swift developers benefit from WebAssembly, they're going to be wanting to get some of that as well. My gut feeling is that the JavaScript language itself will start to move towards some of the TypeScript concepts to allow WebAssembly compilation. If you've been following the way that TypeScript has evolved over time, TypeScript has deliberately stayed on a relatively convergent path with the JavaScript language itself. I have a feeling that some of these features, typing for example, might become a first-class feature of JavaScript in order to allow us to compile to WebAssembly. Finally, I guess regretfully, I do honestly think JavaScript's popularity will decrease a little bit. Is anyone going to throw anything at me quite yet? No, maybe leave it a little bit. I'm a big JavaScript fan myself, honest. But I do honestly think JavaScript has got a monopoly at the moment, and the web platform is ubiquitous. I think it's a safe bet that JavaScript will start to have a bit of a fight with some of these other languages. But at the same time, I think the reach of the web will increase even more so. I think through progressive web apps. So progressive web apps are currently talked about mostly within the context of mobile, but progressive web apps make a lot of sense on the desktop as well. So I think a combination of progressive web apps and the ability of WebAssembly to allow you to do computationally intensive, complex operations will mean things like Photoshop, for example, will become a progressive web app. I think things like AutoCAD, the AutoCAD team already are looking at WebAssembly. I think the ubiquity of the web will increase, or the ubiquity of JavaScript and WebAssembly will increase and move more onto the desktop. So yeah, that pretty much brings me to the end. WebAssembly and the death of JavaScript. And I'm going to say, no, it's not going to die, but I think it's got a real fight on its hands. And if you disagree, you can start throwing things at me right now.